Welcome back to LaVand Media. Yes, during certain periods in Earth's history, higher atmospheric pressure and elevated oxygen levels coincided with higher water coverage, creating conditions that supported larger and more complex life forms. Throughout Earth's geological history, the amount of oxygen in the atmosphere has varied dramatically. In the early stages of Earth's development, there was almost no free oxygen. It wasn't until the Great Oxygenation Event around 2.4 billion years ago that oxygen began accumulating in the atmosphere due to photosynthetic microbes. Later, during the Carboniferous Period, roughly 359 to 299 million years ago, oxygen levels peaked at around 35% compared to today's 21%. This increase in oxygen pressure coincided with dense forests and swamp ecosystems, extensive shallow seas and high water coverage, and the emergence of giant insects and amphibians, which thrived in oxygen-rich environments. Higher oxygen pressure meant that respiration was more efficient, allowing organisms to grow larger and sustain more complex biological systems. Insects like dragonflies reached wingspans of over 70 centimeters, and amphibians grew to sizes rivaling modern crocodiles. Periods of high water coverage, such as during the Mesozoic and Paleozoic eras, also influenced atmospheric dynamics. More water meant, well, greater humidity and cloud formation, enhanced photosynthesis from aquatic and coastal plant life, and increased oxygen production, especially from algae and cyanobacteria. The combination of high oxygen pressure and extensive water systems created a feedback loop that supported biodiversity and evolutionary leaps. So, in biological terms, pressure actually increases life by enhancing gas exchange efficiency and respiratory systems, supporting larger body sizes and, more active metabolisms, and even allowing for more complex neural and muscular systems. This principle is, well, echoed in modern hyperbaric medicine, where increased oxygen pressure is used to accelerate healing and cellular regeneration. Life in a high-pressure environment, like deep oceans or dense atmospheres, requires major biological adaptations at every level: cellular, structural, metabolic, and genetic. These adaptations, honestly, allow organisms to survive crushing forces, limited oxygen, and altered chemical dynamics. So, let's talk about what we actually mean by high pressure. Hydrostatic pressure, increases by about 1 atmosphere for every 10 meters you go underwater. At the bottom of the Mariana Trench, which is around 10,000 meters deep, the pressure there actually exceeds 1,000 atmospheres. Yeah, that's pretty intense. And just to give you some context, high-pressure environments aren't just in the deep ocean. They also include places like subglacial lakes, the interiors of gas giants, and even some theoretical exoplanets that have really dense atmospheres. Now, at the cellular and molecular level, organisms have to get pretty creative to survive all that pressure. For starters, cell membranes can become way too rigid under high pressure, so these organisms adjust by adding more unsaturated fatty acids to keep things flexible. When it comes to proteins, high pressure can actually denature them, but barophiles, those pressure-loving organisms, have evolved enzymes that are more stable, with tighter folding and fewer cavities. DNA isn't safe either. Pressure can damage it, but these organisms have enhanced repair enzymes and protective proteins to help keep their genetic material intact. Even ribosomes, which are essential for making proteins, are pressure sensitive, so deep-sea microbes have modified ribosomes that resist being deformed. Moving on to metabolism, many deep-sea organisms actually slow things down. They operate at reduced metabolic rates to save energy, since they're dealing with cold, high pressure, and low nutrient environments. Some of these organisms don't even rely on oxygen. Instead, they might use anaerobic pathways or chemosynthesis like oxidizing hydrogen sulfide to get the energy they need. And of course, their enzymes are specially tuned to work best at high pressure and low temperature, often needing less activation energy to get going. It's pretty fascinating how life adapts, isn't it? So, when it comes to surviving under extreme pressure, deep-sea creatures have developed some pretty fascinating structural and anatomical traits. For starters, they don't have gas-filled cavities like lungs, swim bladders, or sinuses, because those would just collapse under the immense pressure. Instead, deep-sea fish often lack these entirely, or they replace them with organs that are filled with lipids. Their skeletons are also super flexible, Bones and shells are either reduced or made from materials that can tolerate high pressures, like cartilage or specially adapted calcium carbonate. And many of these organisms have really compact body plans, which helps minimize the surface area and reduce pressure differences across their tissues. So, let's talk about genetic and evolutionary strategies. In microbial communities, horizontal gene transfer is actually pretty common, and it allows these organisms to rapidly adapt to pressure and chemical gradients. Gene duplication is another trick. Having extra copies of pressure-resilient genes gives both redundancy and a chance for specialization. And, symbiosis is huge down there. Many deep-sea species really rely on symbiotic bacteria for energy, especially when they're hanging out near hydrothermal vents. Now, when we think about life on planets with thick atmospheres or subsurface oceans, it's likely that life there could evolve similar traits. We're talking about slow and efficient metabolisms, pressure-stable biochemistry, non-oxygen-based respiration, and, compact fluid-filled bodies. These adaptations might be the key to survival in extreme environments beyond Earth. Let's look at some real-world examples of high-pressure survivors. Piezophiles, for instance, are microbes from the Mariana Trench that actually thrive at pressures greater than 1,000 atmospheres. There's also Cuvier's beaked whale, which can dive to 3,000 meters with collapsible lungs. Pretty amazing, right? And then you've got Hadal amphipods, which use aluminum armor that they extract from seafloor mud. Nature really is full of surprises. Thanks for joining us at LaVand Media. If you enjoyed this, please like, share, and subscribe to join the tribe.